Okay, so junction rule says we conserve charge. Whatever goes in a junction, that's what has to come out. Loop rule says whatever closed circuit we pick, we have to lose the voltage that was put in. Okay. So let's say I want to simplify this. Right. Hold on. Guys. So I'm going to say my high side is 120 volts. What's my low side going to be? 0. So we're going to say our ground state is 0, or our electricity wants to go to the ground. We're first going to come across 1 ohm resistor. The 1 ohm is going to lead to a junction. That is a 6 ohm and a 48. After the 48, there's another junction somewhere. But after the 6, it splits up, right? To 60, 30, and 20. And then it will come to a 2 ohm. My suggestion is always to work inside out. Now, you will never have more than one parallel branch on the test. You won't have like a parallel inside a parallel.
Really? Mm-hmm. That nice?
Mm-hmm.
That's good.
Yeah. To resolve a parallel section, we take all the branches, invert each branch, add them together, and then do what? Invert it again. So just copy this because that'll probably take less time. So I'm going to replace this piece with a resistor that represents that section. So we would take 1 over 60 plus 1 over 30 plus 1 over 20, and we'll invert that. So 1/60th plus 2/60th plus 3/60th, 10. Yep. Okay, so Dylan, how do I resolve the series? Yep. So I'm going to replace these. So 6 and 10 makes what? 16. And then we do that process again. Back to ground. 16 is 3/48.
Yes.
4/48.
And 12.
12.
I'm sorry,
I can never add, so it's all right. So we just, 15. So now we can find our current. So our total current is what?
8 amps.
8 amps. So that means our 1 is going to get 8 amps, correct? And our 2 will get 8 amps. Okay, so we have 8 amps going in. Our resistance is 1 to 3. So our current should be what?
3 to 1.
3 to 1. So this will be 6 amps and 2 amps. Because the one with least resistance should get the most current. So if I were to take like a voltmeter and get the voltage across this resistor, how much voltage did we lose? Yeah, it's going to read 96. How much do we lose across the 1? 8. Okay. How much do we lose across the 2? So if we take the 8, the 96, and the 16, what do we get? Yeah, 120. So this works. Along that pathway, we go from 120, we lose 8, so we're at 112. We lose 96, so we have 16 left. Back down to 0. So that means across that top section, how much should we lose? 96 as well. Well, if the 6 ohm resistor is getting 6 of those amps, how much are we losing across the 6 ohm? 36. So that means our parallel section has to lose how much? If it was the whole thing has to lose 96. 60. So we're going to start with 120. We don't lose any along the wire. We're going to lose, we said, 8 volts, so we'll be at 112. Still don't lose any along the wire. The 6 is going to lose 36. So that's what? 76? And this one's going to lose, we said 96. So we'll be at 16. And these are going to lose 60. So 76 minus 60 leaves us at 16. Notice all of these are now at 16. We're going to get to the 2 ohm and it drops 16. So we'll go from 16 back down to 0. So we worked off of several principles. The fact that we have to lose 120 across there. It doesn't matter what path we take. And we worked off of the fact that we knew the current was conserved, or rather the charge was conserved. Miranda, did you have any questions still? Okay. So remember Ohm's law. Current voltage drop divided by the resistance. Joule's law, if we use that, we eventually got power is current squared times resistance. And you can combine those into whatever combination you need. Let's see, what else for circuits?
What's that equation where it's like electric potential equals work over charge?
Okay, so the potential, so not necessarily the difference in potential, but the potential itself is the work done to each charge. So we could say the potential energy given to each charge. So when we look at our diagram here, these numbers represent the potential. If we put a voltmeter up here, that would give us the potential difference. So the potential difference across that 6 is 36 volts. But the potential at the 2 different points are not necessarily 36. We're just saying the potential between, or sorry, the difference between those two is 36. So just like with a battery, our difference is 120, but this isn't necessarily 120. It could be 90, and this could be negative 30. It doesn't really matter to us. Kind of like with gravitational potential. I could say, if I have a staircase, I could say this is 0 joules down here, or I could say that's 0. I just have to make sure that this way is positive and this way is what? Negative. So we just shift it so that our ground state is always 0. It's just easier to deal with. What about the definition for current? What's that equation going to look like? Not necessarily electrons per time, but the amount of charge, yeah. Because there's two different currents. There's the real and the conventional. The real follows the electrons. The conventional follows the positive charge. So,
do you like need to know that necessarily?
yes, because what they give you, they might not necessarily. I mean, they may ask which way is the conventional current flowing, or what, something like that. So this side's the positive, and this is the negative. The real current is the electrons, correct? So the electrons will want to flow this way. So the battery's job is to push them to the other side. So this is your real. Oh, wait, I had that backwards. Electrons are attracted to what side?
Positive.
Thank you. So they'll be attracted to the positive. The battery puts in work to push them to the other side so that they'll go back again. The conventional current follows the positive charge, so it'll go to the negative. Any questions here? I'm trying to think of what else there is other than Ohm's law, Joule's law, series parallel. So parallel, what's the same across each branch? Yeah, the voltage drop. What's the same throughout a series circuit? Yeah, the current. What I see all the time, though, is maybe the circuit looks like this. Yeah. And the question may ask, okay, if we add a third resistor, what's going to happen to the current? Well, that will end up looking something like this. Correct? And students will tell me all the time that nothing happens to the current because it's in series and stays the same. What's the misconception there? There we go. So what we're saying is all of them have the same current as each other, but if you mess with the system, that's going to mess with the total current. Very good, Dylan. What else? I mean, and anything else regarding circuits? Okay. What about like static electricity and stuff?
Yeah, like
Yeah. No problem. Ranking tasks, right? What? Okay. So the very first one. Charge rod brought close, blah, blah, blah. The leaves are deflected. None of them are grounded. So essentially these rods are doing what to the electroscopes? It's polarizing them. Does polarization change the charge of an object? No. So every single one is neutral. So we could say all zero. Because remember, induction requires that we ground the object. Yeah. So for induction, it's a process. So first thing you're going to do is bring the charged object near whatever you're trying to induce a charge in. And that should polarize it, right? So where are the electrons going to want to be? Top or bottom? Yeah, it's a positive rod. So they're going to be towards the top. Remember, charge builds up inside or on the outside? On the outside. They want to be as far away as possible. We're talking about the net charge. There can still be electrons in the middle, right? But we're talking about the excess. So that's going to leave this bottom here positively charged. So that's why it repels like that. So first thing we're going to do is polarize. While it's polarized, what are we going to do? Yeah, we're going to ground. So we're going to hook up the ground. And what are the electrons going to do? Are they going to leave the electroscope, or are the electrons from the ground going to go up to the electroscope? What are we charging it with? The positive rod. So is that going to attract electrons or repel them? Attract. So the electrons are going to go here.
So you're still leaving the rod like up?
Yes. So then that's going to leave the whole thing with what kind of charge? Mm-hmm. Does that mean that we're out of protons for the electroscope? Yeah, there's still protons. It's just we have an excess of negative. So once we've allowed the charge to build up, you'll get rid of the ground. So that's going to go bye-bye. Why do we remove the ground first? Yeah, if we remove the charged rod, it's going to go back to neutral, right? So remove the ground first, and then you'll have a nice little charged object. If you keep the rod there, it'll still be polarized, but it'll be charged now. See you guys. So if you use a positive object to induce a charge, it'll induce what kind? And if you use a negative object to induce the charge, positive. For that one, remember for a closed system, the amount of charge stays the same if it's closed. It's like the total charge. We'll say Q system. Now, if we're inducing, that's not true because we're grounding, right? But total charge system is going to stay the same. So that tells us whatever one object loses, another object should gain. For conductors, we said the excess charge builds up on the outside. What about insulators? Where does the excess charge build up? Yeah, wherever that charge is landed. Trying to think of what else. Remember, conductors can transfer charge. If you guys remember with the pie pans, I think for first period it didn't work out really well. But if you have multiple conductors, so if all of these are conductors and we bring something that's charged nearby, we can treat the whole thing as one object. And so it'll polarize like that. But like with the jar, the light jar, if we have an insulator in the middle, that won't be able to happen because the charges won't be able to go across. So they would, if we had an insulator in the middle, we'd probably get something like this. So here, insulated. If we repeat that process, but they're all conductors, probably get something like this. Any other questions on the ranking test?
Could you provide the answers of every problem so that
They're on the last page with explanations.
I guess problems 1612 and 1616 on mastering physics.
Which one is this? What assignment?
The tutorials due tomorrow.
Okay.
I want to see how those are done because they look complex. I could be wrong about that though.
So this is mastering physics. Homework due tomorrow. 16 what?
12 and 1616.
Okay. So mastering physics 16.12. 3 positive particles, blah, blah, blah. So they're all the same charge. That's nice. And they're all the same distance away. Well, if they're all the same distance away, immediately that tells us these angles are what? 60 degrees. There we go. Okay, so it says calculate the magnitude of the net force on each particle due to the other two. Well, if we find one of them, that should be the force, the net force on all of them. Okay, so I'm just going to pick the top one up here. So we're going to have two forces. If they're all the same charge, that it's going to attract or repel. Repel. So we'll have force from the bottom right one, and we'll have the force from the bottom left. Well, if anything's in 2 dimensions, what should we do? Yeah, resolve it. The good thing is, if these are both from the same distance and caused by identical charges, what do we know about their horizontal components? So what are they going to end up doing? Canceling. So we could go ahead and figure out the horizontal components. I'm just not going to care about them eventually. So really, we need to find the vertical component. So we're going to have the force here, which is K Q squared over R squared. This is 60 degrees. And I want this component here. So K Q squared over R squared times what? Sine of 60?
Which should be radical 3 over 2.
Yep. So I'm going to have a component here and a component here. What am I going to, how do I add vectors?
You can either do it in components.
Well, graphically, how would we add?
Put them on top of each other.
Yeah. So essentially I'm going to have a vector that is twice the length. So if one of them is K Q squared over R squared, root 3 over 2, and I add that in, I'm essentially getting rid of that, right? So we get K Q squared root 3 over R squared. Ta-da! Choose the direction of the force exerted on the upper particle. Well, we said the side to side is going to cancel out. So it should be upwards.
Up.
Mm-hmm. Yes, sir.
When it gives you the like charge,
Mhm.
I think that's where I messed up on the quiz. I tried multiplying it by coulombs too many times or whatever. Like, how do you get that to the Q that you actually put in? 'Cause it's like
Okay.
symbol before coulomb, like 10 to the negative 11.
Oh, hold on. I just got out of it. 1 second. Okay, so mine where it says Q is equal to 7.4 microcoulombs. And if you take a look at your formula chart, it tells you that micro is 10 to the 6th. So that's 7.4 times 10 to the negative 6 coulombs. So if I were to plug this in, I would say my K is 9 times 10 to the 9th. My Q is 7.4 times 10 to the negative 6, and I'm going to square that. We're going to multiply by root 3 and divide by r squared, which for me is 0.15 centimeters. So that's how I'd plug it into the calculator. I think in the calculator you can use the e function, right?
Yeah.
So you could say
Easy to
what was the other one? Or did that answer your question, Dylan?
Yeah.
Okay.
So on the quiz,
Mhm.
the reason I didn't try multiplying it again by what a coulomb actually is.
Oh no, that'd be like if you're looking for like the number of electrons. So like if I gave you like 2 amps of current and I wanted to know how many electrons go through in a minute, then we could say, okay, current is the amount of charge in that time, right? So amount of charge should be 2 amps times 1 minute is how many seconds? 60 seconds. So we get 120 coulombs. So if I want the number of electrons, I would say, okay, I have 120 coulombs. I know it's 1.6 times 10 to the negative 19th coulombs per electron. And I can get my number of electrons. And remember the exchange, like the change in charge is always going to be some multiple of the electron. Because they're elementary particle, we can't break them down any further. I think, what is it? Quarks and something else?
I think photons also fall into that category. Could be wrong.
You wanted 1616?
Yes.
Okay. This one's a good one. Okay. Charged electroscope, the leaves are blah, blah, blah. Nearly all the charge resides in the spheres. If the wires make a blah, blah, blah angle, what's the total charge must have been applied to the electroscope? Okay. Well, this is when we really need a free body diagram. So this is going to be Q over 2. Angle is going to be 26 degrees. Well, I'll just call it theta. And then this is linked L. So our free body diagram, what's going to be pulling on the sphere?
Gravity and tension.
So we'll have gravity. We'll have the tension at the same angle, right? And then what else?
The electrical force.
Okay, so if they're both the same charge, are they going to be attracted to each other or repelling? They'll be repelled. So right away we can see a few things. We can see that the vertical component of the tension will be equal to the weight. And we can see that the horizontal component of the tension will be equal to the electrostatic force. So I can say T sine theta is equal to mg, which I think is given in grams, so you'll probably have to convert. And we know T cosine theta is equal to our electrostatic force, Q over 2. Oh, that's not a Q.
Theta over 2.
Yeah. Q over 2, Q over 2, R squared, which would really help if we had R, but we do have a way we can find it. So this is L, that's L. Actually, it might be easier if we do this. So that's L. This is theta. Then R is L sine theta times what? 2.
So R isn't like the radius between them, like.
It's distance from center of charge to center of charge.
Okay.
So 2L sine theta. Well, if I were to divide that by that, this is tangent theta, right? On the left-hand side. Because T over T is just 1. And I get mg 2L sine theta. Square that over K. What is that? Q squared over 4?
Yeah.
And then you can solve for Q. Whatever you guys want to do to solve it. You don't have to do that. Just find Q.
Wait, why did you do that?
Because I can. If I can multiply both sides by whatever I can divide, right? So if I divide one side by t over cosine, I have to divide the other side by t over cosine?
Yeah.
Well, isn't that t over cosine? Or sorry, t cosine? So yeah, you can,
Like, why did you choose to do it that way?
because I could.
Yeah, I know, but I don't get that.
It doesn't necessarily mean it's the right way. I don't have a particular reason for doing that.
Okay.
Because I could just say, okay, there's sine theta, so I can substitute this in for mg over t and go from there. It's whatever you guys want to do. So I think we're given m and g, right?
Mm-hmm.
So if you're given m, you know g, you know theta, you can find the tension, plug that in here, and solve for q. So it's whatever you guys want to do. So however you guys want to solve it. The big thing that I need you guys to understand is the relationships going on with the forces. So it's can you apply first law with electrostatic forces? Any other questions? Okay.
Do we just have to stay like, or can I ask you about like other things?
You can ask me about other things.
You know that one test question with the ladybug and whether or not the ladybug like applied a torque on the disc?
Okay, so I cannot talk about that directly and be able to post it online because it is a secure question, but I can give you like a reasoning behind something similar.
Because on this review classroom, there's a practice test or rotational motion problems key.
Okay.
Or with keyframe, the number 11 has something kind of like that, I think.
Okay, so let's take a look at. Okay, so we got like a merry-go-round.
Yeah, like things like this. I just
Okay. So I'll do several different scenarios. That way we're not addressing that particular question. Okay. So let's say that the merry-go-round is spinning about this axis and in this direction. So we're going to talk about this as the merry-go-round system and the person merry-go-round system. So two different systems. So let's say that the person starts walking this way. Relative to the ground, if the merry-go-round originally was going, let's say omega naught, is the person going faster than that or slower than that relative to the ground? Faster. So as a system, the person and the merry-go-round, if there's no external torque, what can we say about the angular momentum? If there's nobody coming along and pushing on the merry-go-round or pulling on it.
Well, because
Yeah, it's conserved. So there's no change because there's no external torque. So that means if the person's angular momentum increases in that direction, what's going to happen to the angular momentum of the yep, because we have to stay consistent. Okay. Now, if we look at it just the merry-go-round system, we said that its momentum has to go down. So what's going to happen to the speed? Yeah, so it's going to lose angular speed. Well, if it loses angular speed, it's going to lose momentum, just like we said earlier. What causes a change in momentum? Work or impulse?
Isn't it either of them? Like technically?
Not necessarily. I can show an example where it's not. Huh?
Impulse?
Impulse. So that would be force times time, but we're talking rotational motion, so not force, but torque. So if it's slowing down, we have a change in momentum. So we have to have some sort of impulse, which means we have to have some sort of torque. But third law says that if the person's exerting a torque on the merry-go-round is on the person. So let's say the person starts walking the other way. What's going to happen to the person's momentum then? It's going to decrease, so what's going to happen to the momentum of the merry-go-round? Increase. Well, we still have a change in momentum for the merry-go-round. It's just positive now. Or, well, it's just gaining in whatever direction we said was positive. So we still have to have some sort of torque. Another thing the person can do, they could walk like towards the outside. As a system, the angular momentum can't change. So if we started out with some moment of inertia for the whole system, so moment of inertia for the merry-go-round plus moment of inertia for the passenger, and the initial. Well, as the passenger moves out, what's going to happen to the passenger's moment of inertia? So what's going to happen to the speed? It decreases. So if we go back to the merry-go-round, its moment of inertia stayed the same, but we said omega went down, so it had to have a change in momentum. So if it has a change in momentum, did the person apply a torque?
yes.
Absolutely. So that's one of the big ideas for AP1. I don't know if in chemistry if you talked about AP, like big ideas, but interaction. Causes change. There we go. So like what causes acceleration? Yeah, it has to be unbalanced, right? What's going to cause a change in energy? Work, which is a force that is what? Yeah, it's got to be parallel, right? What's going to cause a change in momentum? Impulse. Or Gympulse, just silent. And we said that that's really just second law, right? F T is equal to M delta V, which is really F M A. So that's the big thing here. What is your system? So if your system includes the object that's applying torque to the other, then there's no external torque, it's internal. So everything would be conserved, because if it's internal, one's going to have a positive change and the other one is going to have a negative change. So that's what causes that those conservation laws. So you just have to ask yourself, when does that apply? Like if I have a table.
I don't know why, but I thought the person, like whenever they would move, they'd do like an external torque. Like because it's relative to the disc.
Yeah, so they're applying a torque relative to the disc.
Yeah, but I didn't look at the system.
Yeah, so if we're talking about the whole system, there's no external torque on the whole system. So yeah, if I was asking about the person, you could say, yeah, the merry-go-round is applying a torque because the person is slowing down or speeding up in that general direction. Let's say I have a table and I attached a ruler to the table, and I've got myself like a quarter or something, and I flick the quarter at the ruler. What's the ruler going to do? Yeah, it's going to swing around. Well, as it swings around, this hinge here, this pivot, is going to be applying an external force. So can I use conservation of energy? Well, we kind of have to ask ourselves, okay, it's applying a force, but what's the distance necessarily? Yeah, if I say that pivot is very thin, we can treat it like it's 0. If I say it's bigger, then we have to ask ourselves, okay, how much friction and how far is it going around? But generally, we can use conservation of energy. But if we want to know like how fast it's moving around at the beginning, like if we want to know that speed here when it collides, yeah, we need to go with momentum. But the question then becomes, angular or linear? Well, a change in angular momentum, we said, is torque times time, and a change in linear momentum is force times time. We already said we're going to be applying a force at that hinge. So am I going to conserve linear momentum, translational momentum? Well, what does the change need to be to conserve it? 0. So if I have a force there, yeah, there we go. But the torque, though, is the force perpendicular to the arm? Yeah, because its distance from that pivot point is what? If the force is being applied at the pivot, it's 0. So this whole term would be 0. That's not a 0. So then what's our change in angular momentum? 0. So we could use conservation of angular momentum. So that's what you're asking yourself. What is conserved here, if anything? So identify your system. Ask yourself, is anything acting on it? Or are the objects just acting on each other? Any other questions? Know that, for a graph, this could be base times height, base times height. So this would be your area for a force distance graph. This would be your area for a force time graph. Anything else? Okay.
I heard that kinematics are going to be blended with other
Yeah, because kinematics is too easy.
Huh?
It's too easy.
Okay. How do we know that it's blended though?
Basically, you look at the problem and ask yourself, what do I know? What can I use? Basically, if you were, like, let's say something broke in your house and you had your toolbox, you're asking yourself, okay, what's broken? What can I use to fix it? That would be the same process here. You'd look at the question and ask yourself, is this an energy problem? Is this a work problem? Is this a momentum problem? So if it was kinematics, all that would be mentioned would be speed, acceleration, time, distance, maybe. You wouldn't really need mass at all. Right? That never appeared in kinematics. We did a lot of graphing with kinematics. So like if it was position time, what was the slope represented or representing?
Velocity.
Yeah, the velocity for that particular like slope, right? For velocity time, what did our slope represent? Yeah, the acceleration. What did the area represent?
Distance.
Yeah, the displacement. So it doesn't give us a particular position. It's like anybody here in calculus? Okay, yes. So that's why when we integrate, we tack on that constant. Acceleration time. No, maybe it looks like that. I'm not saying the graphs are related to each other. I'm just drawing something.
Yeah.
What's the area underneath? Excuse me.
Velocity.
Yeah, change in velocity. The slope is jerk, but you'll never need to know that. Or at least not for this course.
In pre-AP though, we did do like magnetic fields.
Mhm.
Do we have to know that?
No, all fields except for
Gravity and
Like
electricity.
the
yeah. You don't need right hand rule for this class.
Cool.
So the only things we cover for fields are inverse square law. That's pretty much it.
Really?
Yeah. So we don't need like potential lines or anything like that. We don't need direction for fields or. So you can ignore fields at will. Otherwise, we'll just calculate like the strength of it at a certain pot, like 0.2.
That's good.
Anything else?
Mastering physics one, the last one we worked,
Mhm.
cannot get the right answer. I'm on my last
Help me here.
Well, if you want to know what I did, I broke down the problem and I found out that, have you tried plugging in the formula 4L sine theta over K? I'm not sure if that would work, but to do one.
Okay, so let me go back to the relationships we found. So these two here. Okay, so we're looking for Q. So I'm going to solve this bottom one for Q just to isolate it. So we'll get 2L sine theta squared T cosine theta K Q squared over 4. And that's going to be 4 as well, right?
Yeah.
Okay, so we'll get rid of that square. Q squared 16L sine squared theta T cosine divided by K. And then we know that T, based on this one over here, is equal to mg sine theta. Should be getting sine cubed though.
What was wrong with the other one where you just divided them? You got like
Oh no, I see what I did. angle's at the top, right?
Yes.
So T equals mg over cosine.
The angle's at the top, so this is sine,
Yeah.
and that's cosine. So I have to switch. I led you astray, Dylan. I'm sorry. So then swap that for sine. So we get over k, and we said t was mg over cosine. And then we're going to square root the whole thing. So we get
Is theta just the one side, or is it both of them together?
it's just one side on the problem.
Could you share that equation again for a brief moment? I've got it now.
Is it L the length of the string, or the length of
The length of the string. So mine's reducing to 4L sine cubed times mg over k cosine theta. So that's nice and pretty, right?
I mean, I guess.
I mean, you
Yeah.
could do it
Not
sine
bad.
theta
Yeah.
with the sine theta out and in of the root, right? Because it's a cube.
So you could take sine over here for no reason, I guess. And then
This could
then
be
that's
a
now tangent.
Wow.
Still have the